we'll attempt at doing that real quick. So how to get away with a murder? I'm in incognito. Okay, so that's not my that's not, how can that be? That's not my search history. I promise you guys. How to sell drugs online fast. How to be single. That's so fucking crazy, man. How? So how to do QFT? No, not QFT. Fourier transform. Visual introduction. Blah 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 blah. Better explain the Fourier transform. Okay, so these two equations, yeah, X rather than jumping the symbols. The key idea first hand is spending. Give it a smooth it finds the recipe. I like that. Two. Okay, give me a second, guys. We are back. Sorry, guys. There's a call. So, what about? I'm just trying to go too fast. But let's do that. So, I want to get to the point. Maybe that whole explanation is a bit too. Discovering the full transform frequency recipe. Add up contributions to this frequency from each spike. I get. Okay. Yeah. That's. I think I get what this means is. Yeah, but how do I have a new keyboard, new everything, and nothing's working now. I can't even zoom in. Oh, there you go. So the E thing, right? And it's a complex exponential, so that's why it's circling. So, and that's how I guess you're adding all these components and have some kind of like weight to it. I don't want a long introduction. I want to kind of get to the gist of it. And actually, I want to do the inverse, right? How to do the inverse Fourier transform. The inverse Fourier transform is, so it's an integral. So two commonly used definitions of Fourier transform of xt. it's kind of it almost feels like it's one of the first times where the actual Wikipedia is just going straight to the thing, and then some but again, I might want to interpret what these things mean, right? So I'm let's see. If we have a function from the real side satisfying certain conditions, we can use the convention to transform that. So it's an integral. The Fourier integral theorem. The most common statement of the Fourier inversion theorem is to state the inverse transform is an integral for any integral function. And that kind of comes, I think that comes from the fact that I just saw that the actual Fourier transform has this form, right? It's so you're in a way finding an approximation. Not an approximation, you're building up a function out of these things. And so, but why is it an integral? That is going to be complicated. Why is it an integral? You know, maybe I should actually read. Maybe I should actually read these. But do they talk about the inverse here? No. But I should maybe. It's just. So look at this. So the Fourier transform of a function gt equals, whatever these gf, and this is the integral. So they're both integrals. That's interesting. Why? Why is the Fourier transform an integral? Because it exploits properties of the sine and cosine to recover the amplitude and phase of each sinusoid in a Fourier series. The inverse Fourier transform recombines these ways using a similar integral to reproduce the original function. It's pretty cool how accurate actually they highlight the specific answer that I'm looking for in the in Wikipedia, right? So introduction. Yeah, okay, let's do that. So, although Fourier series can represent periodic wave forms as the sum of harmonically related sinusoids, Fourier series can't represent non-periodic waveforms. Interesting. Okay. However, the Fourier transform is able to represent non-periodic waveforms as well. Okay. It achieves this by applying a limiting process to lengthen the period of any waveform to infinity, and then treating it as the periodic waveform. In the study of the Fourier series, the Fourier coefficients represent the amplitude of each harmonically related sinusoid. So I guess it's just you express it as a sum, right? So you have like a weight or an amplitude times this exponential that is basically the thing that oscillates, and then you add a bunch of them, right? represents the amplitude and the phase of every sinusoid. Oh, sorry, I got lost. Phase of every sinusoid present in a positively non-periodic function f. So, use of complex sinusoids to represent real sinusoids. To simplify the math, it is desirable to write the Fourier series as a sum of complex exponentials. Each complex exponential or complex sinusoid of whatever this frequency is can be expressed using Euler's formula as the sum of a cosine wave of frequency and a real component and a sine of wave also with the same frequency for the imaginary component. So you have these. Expressing real sinusoids as complex sinusoids makes it necessary for the Fourier coefficients to be complex valued, but it has the benefit of compactly representing all necessary information about each frequency. The usual representation of this complex number, that is, its magnitude is amplitude, and the argument is the phase of the complex sinusoid for that coefficient. These complex exponentials may have negative frequency, for example. Real sine and cosine waves can be recovered from the complex exponential representation of the sinusoids. For example, a correlative to Euler's formula allows expressing cosine and sine waves as either the real arbitrary part of a complex sinusoid or as a weighted sum of two complex sinusoids of opposite frequency. Consequently, a general form of any real sinusoid with frequency, whatever this is, phase shift, theta, and amplitude A can be expressed as the sum of two complex sinusoids of opposite frequency, but equal magnitude. Oh, God. Oh, that's pretty nice. Okay, I see what you're doing there. Because these things cancel out, right? What? No? Yeah, exactly. The imaginary components cancel out. Okay. And all this just to be able to express that thing in a compact way with an exponential, right? So what you're saying is you're basically, this whole thing is like, okay, so this is, it's pretty nice how much like creativity goes into this stuff, right? Like figuring out how to represent things so that they become, you know, easy manageable in a form, in a sort of a formal way. Because basically what you're saying is I have frequencies, right? Let's say I'm just going from, you know, from the frequency domain to the periodic domain, right? So you have a frequency of like 5 and a frequency of like 10. And so, and what you're trying to do is like, you're trying to represent that. What you're trying to get is you're trying to get the wave that's the sum of the two sinusoids that would have that frequency. So first you gotta think of how do you express one sinusoid with a given frequency, and then you say, well, it's just that frequency, put into a cosinus or a sinus function, right? I guess that's it, right? So if I go to the, what's that thing to plot? Like, there's like a, plotting or something. There's like an app, or there's something that is like a Desmos. I think Desmos is a good one. I don't know. I have never really found any. So let's say if I just say cosine of x, right? I get that. So this is frequency, I guess if I say cosine of pi x, right? Or that makes the frequency 1, right? So it's like it does one full cycle. And if I just say cosine of like 2 times pi times 5 x, that's like 5 times faster, right? And so what I wanna, if what you wanna do is you wanna kind of have that plus that, right? In a way, can I not? Yeah, exactly. What? Sorry, I'm using that shouldn't be zooming out like this, like that. That's the sum. Okay, where was I though? Down with this, down with this, down with this, down with this, down with this. So but okay, you're trying to find a way, like yeah, of course, and you still have like an amplitude, right? So if I just want to say, I don't know, 3 times, right? So that's the amplitude in here. If I want to express these, like you can express that with these kind of, yeah, because if you use a complex exponential, which by the Euler's formula can be expressed like that, and then you use the same but with a negative sign, basically the complex thing will cancel out, right? Because one is plus, one is minus, and so you will end up with twice the cosinus, which then you get rid of twice of the 2 by dividing the amplitude by 2. I don't know if you can you see this? It's probably not because I have a big screen, but you probably can't see. And so it's a smart way to say cool. So you can do it like this, right? That's one way to do it. But why? Why are we doing it like that? Okay, so I understand why. This is just something you can do it. Yeah, cool. So a real sinusoid can be expressed like that with this. And to avoid the use of complex numbers and negative frequencies, the sine and cosine transforms together can be used as an equivalent alternative form of the Fourier transform. I don't know what that means, but whatever. Fourier transform for functions that are 0 outside an interval. No, that's not what I want. I want to understand why. I want to understand why is it an integral? Why? So the Fourier transform is an up here by adding a circumflex. Okay, yeah. When it's time, often is t instead. The transform variable represents frequency. That's introduction, cool, yeah, but then what? Like, there's a close connection between the definition of Fourier series and a Fourier transform for functions f that are 0 outside. I'm not interested in that. I want to understand why. Why is it an integral? And an integral of what? So you have your function. And you multiply by these, and then you integrate. Why? What does this product And what is this? Isn't that a set of frequencies? Isn't that a set of frequencies? Yeah, I know all the stuff, the full transform. Frequency and frequency. Separate the full signal into time spikes. It's not an integral, then it's just a sum. Can we see an example? Can we see an example? Then I'll go through the inverse probably in the next session, because I think I've got 10 minutes left. Fourier transform example. I mean, is it just as simple as like I'm so pissed with the, I already don't know anymore whether, I mean, how do you even get spikes? It's just like I'm very pissed with the fact that like, is the Fourier transform this way or that way? I want a fucking example. Okay, so we'll break apart a time signal and we'll return information about the frequency of all sine waves. Yeah, but that's the, for sequences of evenly spaced values, the discrete Fourier transform is defined as, that's a discrete Fourier transform. That's a specific Fourier transform algorithm, or what? FFT. Let's write some code. Okay, so first we define a simple signal containing an addition of two sine waves. Yeah, okay, cool. So that's what, I mean, that's in a way what I have here, right? So you plot that. In order to retrieve a spectrum of the frequency, I say, no, we must take a, you see, that's the all the way around, but whatever. So the FFT is actually, the Fourier transform is from these to the from the periodic domain to the frequency domain. That doesn't explain the math. I'm trying to understand why is it that it's an integral, and why is it that you're multiplying f of x, right, with just that. I mean, we can make an example ourselves, right? Why not? We can just say, let's just say our, let's just say the function we want to do the Fourier transform of is just an actual pure sine wave or cosine wave, right? Like this one. So that it's literally should give me like 1, right? So if I do these, why do I need to multiply these by that factor? So well, I don't know. I don't know what these things are. That's, I guess, what I have to find. For all of the frequencies belonging in R. God. and what? Like I can do the integral and what? I'm not going to be able to plot this in any meaningful way. But like the integral, so the integral of cosine is minus sine, is sine or something like sinus or minus sinus is sinus, right? Yeah. So if I would just say like, wait a second. If I just say that I have the integral of like cosine is my function, and then I do this e to the, you know, and this like, what was that? Minus 2 pi ix and these frequencies, minus 2 pi ix and then the whatever frequencies is it, right? If this is just the integral, right? I mean the integral of these, okay. The integral of this, that's a bit tricky, right? Because I actually have to, it's interesting. Because it's the product, the what is the chain rule in this case? I think, isn't that like integral of the product of functions? Integration by parts. Okay, there you go. God, yeah. Almost forgot about this. And so I can assume that that this is this, right? So but you see what it does is it takes that okay, so it's okay, so it's like ux so the integral of that, yeah. So I basically, what I should do is, where's the pain thing? So it's like cosine of x times the integral of these, which is the same, right? So it's plus, and now it's like the integral of not plus, minus. Yeah, but that doesn't help me, does it? At all? How does that help me? Minus what? Minus the integral of like sine and then this thing, right? Whatever it is. But it doesn't. But if you can, I'm trying to understand is if you do that repeatedly, it actually gives you something. And that's weird. It's actually weird. It does build up like as an expansion, right? But it's still like you have this cosinus here, so I'm lost here. I'm definitely lost here. Because then the next step here would be like, you know, sine of x, and then all this gibberish, and then minus cosine, and then you're kind of, it's a loop, right? So cosine plus, it's like cosine of, and then times this thing plus sinus, and then times this exponential, complex exponential thing here. What if we analyze these, right? So this is basically saying cosine of x times, and this something here, to be honest, it can be expanded, right? So it's like, yeah, but there's a complex part of it, because that's like cosine of all that stuff plus I times sine of all that stuff. So it's cosine squared plus cosine times sine times I, like, I mean, yeah, but okay, but cosine, that's just, okay, no, that is something else. I don't know, man, I don't know. That's not easy. Why is it an integral? It seems to behave the way that we want to, right? Because if we think about if we think about composing as like, you've got all these exponential things in there, that give you that frequency things. Yeah, and that it kind of like, okay, not that easy. But I don't know why. Why is it why is it an integral? It's just for practical reasons, I guess, because it actually, that expression generates these in a way, right? Cool. More on that next time, I guess. I gotta go on, yeah, because maybe I should just take a look at the discrete Fourier transform or something like that. Well, I should properly learn these. I should definitely properly learn these. The discrete one is probably an easy one. I mean, I know I understood the quantum one, which is a version of the discrete one. So, and again, remember, all this is because I'm trying to do that exercise, which is basically we wanna do the Fourier transform of these, right? And then do the probability density function calculated, and then you want to check that what happens with this momentum, right? That's a whole other story. But yeah, first we need to figure out how to do an inverse Fourier transform or a Fourier transform at all. And I should just probably stick to trying to find why is it an integral? Why? That buggers me at the moment. I can probably go through these, although, oh god, it's long, and I think a lot of this stuff is just basic, right? So, in a way, I get this. I get why is that, but then I don't know if this is. So this is this kind of like, let's build a function out of a composition of sinusoidals. Totally makes sense. But then I don't understand, what is these? What the fuck are you telling me? Is this just the continuous version of it? You're just like doing the sum of, because at the end of the day, what the integral is it's sort of an infinitesimal small sum, right? But I have f of x. How come? Like, I don't know. See you next time.